Hello everyone, welcome to today's webinar. So hope everyone's doing well and okay. We'll just leave it a few minutes just to let everyone join in. So yeah, we've got some people coming in now. Numbers are climbing up. Hopefully you can hear me, hopefully you can see me. Let me know in the chat if there are any problems. But we'll get cracking as soon as a few more people join us. So I'm from the UK, if you didn't guess by the accent, just west of Birmingham. Where are we all from today, if you wouldn't mind me asking? Just while we're letting people join in, I've chucked a quick poll in the chat. So just to give us an idea on who we've got on today and how we can tailor this to best suit your needs. Looking at this, we've got everyone. We've got people from 0 to 1 to 20 plus and all in between. So got a nice range of everyone at the moment looking at this. We've got Sean from Colorado, Dane from Colorado. I actually had two Canadians join me on the one this morning, which was for the European time, but they were dedicated and joined me at 6 o'clock in the morning. So we've got California. I'll leave it another 30 seconds, then we'll go off just to let the last few numbers coming in. They're just tailing off now. Hi Ryan from Canada as well. So yeah, got a nice range of different people from different locations. That's always nice. Okay, so I think let's get started. So thanks everyone for joining. Really appreciate your time here today. Hopefully you know what this is about. So we're going to talk about using your digital probe with Fusion 360. Hopefully we're going to show you what you can do with the probe, why you should be using it, and hopefully give you some top tips on mainly how to save you money and time and make you more efficient. Please be as active as you can in the chat. This is going to actually drive with all of you out there. I used to think that a good presentation was getting from start to finish in the time allotted. I've now realized that success is by how much the viewers get out of it. So please, I'd much rather you ask the questions and I run out of content, run short on content, than you don't get your questions asked. So please be as active as you can in the questions and we'll try and keep up and do what we can. So what are we going to cover today? Well, the first thing we're going to look at is the canned cycles on our machine. How do we interact with them? Why should we be using them? And what are they going to do for us? We'll look at WCS setting or datum setting. We'll look at toolware, and we'll look at what we can also do, bringing some of that information back into Fusion as well. We'll take a quick look at what we call non-prismatic, so inspect surface. Some of you might have heard of this before, but it's our way of basically being able to place a point anywhere on your machine and inspect it. So really important and can be quite powerful. We'll then look at part alignment. This is where we're actually going to use those inspection results to do some really complex alignments. I'm going to get more into that. Manual measure, we're going to finish on, and it's probably one of the coolest things to see. So stick around for that one and you will not be disappointed. A quick thing, you might notice that plug on 3 of the different items. These are in our extension package. So hopefully those that know, Fusion comes at a base price, and then you have extensions that bolt onto that. The idea then is it's flexible access if you need it, and if you don't need it, you're not paying for it and not using it. So we'll talk more about how that works and examples around that later, but I like to be as open and upfront and honest as I can be right from the start. I don't want to get into this and someone goes, oh, is this extension? Is it not extension? Probe geometry, inspect surface, and part alignment are extension. I'll be showing you Pro WCS and manual measure, the two things at the start and end. They're not in the extension. So hopefully you can follow on and keep track on that. So who am I? So my name is Richard Stubley, as you might have guessed from my little introduction. I am based in Birmingham in the UK. That's actually where 300 and something of our developers that purely work on Fusion are based. So we've got a real strong development team over, well, more than one team, of course, lots of teams for 300 people, teams over in Birmingham in the office. I came through the apprenticeship route. So I spent 4 years as an apprentice, you know, being told all those tricks. Can you go to the store and can you ask for a long wait? Can you get a jar of sparks for the grinder? I'm hoping these are translating over to the same tricks that are played over in the States than what they are on this side of the pond, but you get the whole picture. The best one that I ever had was I was in the metal forging industry and I was in the inspection side, and I had some big, what we call tongs to pick up the hot forgings. And every time I left them on the cooler, they went really tight. I didn't realize that the guys were putting them under the forging hammer and knocking the rivet down and making my tongs all tight. So that was the that they got me on that one in my apprenticeship. But it'd be interesting if any of you guys have been apprentices, or any of you gals, anyone out there, any tricks played on you. And I'm always interested to hear stories of what apprentices had to go through. I dabbled in injection molding, didn't like it, came back to CNC machining. When I joined Autodesk, because of my background in CNC machining and quality control, I fit in quite well to have a specialism in metrology. That's probing and inspection, not meteorology, the study of weather. My wife always thinks that I was a weatherman until I explain that no, I'm metrology, not meteorology. On a personal note, I like building cars and mountain biking. So you can see on the right-hand side, my Cobra that I spent the last 4 years building was finished in October, and we're now waiting for some nice weather. So we might even get one day of nice weather in the UK this year, and I can take it out for a quick spin. So enough about me. Let's have a quick look at Autodesk. What do Autodesk do, and why might you be here today? So I've still got friends that still think that I work for AutoCAD. I don't work for AutoCAD, I work for Autodesk. So it'd be interesting, again, if any of you out there think we still work for AutoCAD. But the whole thing, what we're trying to show here is there are three main strands to Autodesk. There's the media and entertainment. If you've watched a film or a movie recently, there's a good chance that our software helped make that. Architecture and construction. If you're in a building at the moment or you're looking at a building, there's a good chance that we had some part to play in that building. And then the environment that we normally live in is in manufacturing and design. So again, pick a component, any component, and I bet we might have had some part to play in that component. But the whole principle of what we're trying to show you here is when you actually invest in an Autodesk product, you benefit from all these strands. You know, our media and entertainment, groundbreaking in rendering and visualization. You know, the architecture and construction, me as a mechanical engineer, I think of as a large data set as about like a meter. You know, a meter in construction is negligible. So you are really benefiting from all this technology that we have at Autodesk inside of the products that you have then. So you're buying into a lot more than just the product. It's all the technology that surrounds us and all those years of experience in there as well. So that's a little bit about Autodesk and how they are. Hopefully you can see now why you should be joining us on this journey to make anything. So let's dive right in to setting your datum. So this arguably is probably the most important thing on a machine, or what a machinist can do, and that's setting up a datum. Because if you don't do this, well, good luck in machining a part, because the machine's not going to find it on the bed. So that's really important. We're talking about CNC machines, computer numerical controlled machines, very different to the manual machines of the past. You can't just put a part on a bed and then the machine knows where it is and will machine it. Some of us might have seen the recent news about different machine tool vendors putting laser scanners on machines. We're still a little bit away. So from today, we still have to set a datum on our machine. So on the left-hand side, you can see a 3D taster and an edge finder. This might ring some bells with some of you of how you currently set up your jobs, or maybe you know this from previous experience of doing it manually and how much of a pain this can be, I would probably go as far as saying half of all crashes can be caused by incorrect settings of datums and tooling. That would be my guess from my experience. I mean, I've put my hand up here. I've definitely crashed a machine before by setting the wrong datum. I think I caught it just in time before serious damage, but the tool definitely went. Be interesting to know again, anyone out there had any similar experiences? Can you vouch for how important it is setting a right datum? So traditionally, you'd set a datum by spending a lot of man hours or person hours or machinist hours in probing and setting up on the machine to find where that block of material is. This was all well and good. The problem is people hours are very expensive. You know, the whole point of what we're trying to do is provide you with a software solution that's more economical than people power. And that is the long and short of it. You know, if you could program parts quicker and cheaper by hand, you would, but you just can't. There's no way that you'd be able to machine, one second, this mold that I'm holding up here. You know, you've got to think that toolpath probably took about 3 minutes to calculate. I challenge anyone out there to write that surfacing toolpath in 3 minutes. And that's the whole point of it. We're trying to provide you with a solution that is cheaper than doing it by hand. And that's exactly where probing comes in. We're going to provide you this rounded solution that's going to allow you to use the probe in ways you never imagined and free up your machinist's time to make you more money by looking at the process, optimizing your speeds and feeds and your cycle times, not standing in front of it, twiddling the hand wheel. That's not what you want to be paying people to do. So setting up your datum, you can use a probe for that. But look there, we've got 9 lines of NC code. Right, we all probably know T1M6. We all probably know G54X0Y0. I, unfortunately, and hope it's my job, G65P9832 is to turn the probe on. P9810 is a protected positioning move. Now I'm struggling. I would probably honestly not have known that P9814 was a boss measurement cycle without seeing it on the screen. You don't want to be, again, you don't want to be looking through manuals every time you want to use your probe. You want to be able to do this from inside of Fusion quickly and efficiently. And let's have a quick look how fast we can make those 9 lines of NC code to set up your machine. So let's jump into Fusion and let's see where we're going. So this is the part that I've got on the machine. I tend to model up my stock, so it's just there. I'm going to go Pro WCS, that's 1 click. Second click, top of the face. Third click, OK. 3 clicks, and I have now got effectively those 9 lines of NC code. I haven't had to know what G65P9832 means. I don't want to know, if I'm honest. I'd much rather know interesting things than that. But in 3 clicks, I've now got a toolpath in Fusion that's going to allow me to set my datum. How much more efficient is that than you paying your engineers or yourself to actually sit there, look through a manual and program this by hand? So that was how easy it was in Fusion to do. Let's go back to the PowerPoint and just see why are we going to want to be doing this. So there is something that we need to clarify here as well, is what's the difference between setting a datum and refining a datum? Now, what I spoke about previously about setting that part up, the machine doesn't know where that part is. So you need to put the datum on the block of material where it is in Fusion. We can't just find it anywhere in the bed because we're driving the probe absolutely, not incrementally. We need to have known a good location for that datum. We can be, you know, around 1/4 of an inch, you know, with a bit of approach and retract and make this work, but it can't be, you know, 10 inches in the wrong direction because we won't find the part. So what I like to say is we're actually refining the datum from Fusion. We're not setting the datum. So you're probably now going to say to me, well, why do I want to do this? Because I'm doing one-off jobs every time. And if you're telling me you have to still set the data manually and then you refine it from Fusion, well, I only make one of every job. Well, valid point. That is a valid point. Let me show you something that's going to hopefully blow you away, that what you can do now. I'm now going to show you a way that you can stop having to set datums on your machine. So this is the way the probing looks. Hopefully you've all seen this before, but for some of you out there that might not have seen this, the probe's going to touch the one side, come over, touch the other side. That's going to set the X direction on this machine. It's going to do the front to back. That will set the Y. And now it's going to touch the top and set the Z. So those 3 probing moves, that's done in 2 toolpaths in Fusion. That's now set that part up. How much quicker is that than your machine is standing there? And the key thing is your machinist is now doing something productive. He's earning you more money. You're earning yourself money if you're doing this yourself. You're not having to sit there with the hand wheel. We've even got one. There you go. A few sound effects there for you. The hand wheel to the left of me on a HAS simulator. You're not having to do that. You're off being productive rather than twiddling that hand wheel. So what's this got to do with blowing you away with not having to set your datum anymore? Well, we're going to talk about something now, a fixed datum. So if I can have a fixed datum on my machine bed that I can then represent from inside of Fusion, you never have to set your datums again. We're still going to probe the parts to make sure they're in the right location and set them up, but we're going to use that fixed datum to get us as close as possible within that approach distance of the probe, and the probe will then find it exactly where it is. And we do this by something called override driving WCS. That's the tool we're going to use in Fusion. Let's see what this actually means on the machine tool though. So what we've got there is we've got 4 different components. We've got vice in the top 2 components. We've got a vice with a set of soft jaws. We've then got a vice just holding onto a block, but the block's tilted. We've then got 2 custom-made fixtures at the bottom. But you might notice the datum on all of these is coming from that base plate. Yes, we've got posh, lang, quick change systems, doesn't matter. All you need is a fixed datum on your machine that you can represent in Fusion. Be that the corner of a jaw of a vice, if it's a fixed jaw vice, not a moving jaw vice, or be it you actually just bolt down a feature onto your bed that you can have in Fusion. What you're going to see now is the machine's going to be commanded from all of these positions. And that's the really important one there. The machine's going to go, and it's going to go from all of those. We've still probed each part. Now, I hope you're following on. Let me know in the chat if this is not becoming clear, and I can definitely explain more around this. This is a really heavy topic, but I wanted to cover it because personally, I think this is going to save you the most amount of time and money on the machines, and also reduce the risk of crashes and problems. So I know it's a heavy topic, but I really think it's something that you need to know. We're going to use override driving WCS. Normally, if I program from G54, so you see my setup here, what we've got, this orange circle, I've got WCS1, that's G54. So normally what would happen is I'd set G54 at the top of my block, I'd then probe that and update it a little bit, maybe 10 thou to the left, 50 thou to the front to get that set up just right. So I've used G54 to guide my probe in. I've then updated G54, and then I'm going to machine G54. This works brilliantly. However, G54 now is no longer in the perfect position. It's in this part's position. So if it goes 50 thou to the left, what about the next part I put in? Do I want that to reference the perfect position or the last part's position? We're using the current methods I'm guessing you're using. You're referencing the last part rather than referencing the perfect position every time. Now, this means that you can have something called creep, where if you keep moving the part slightly to the left, if you go 10 thou to the left, well, after 10 parts, you're now 100 thou out. That's quite a lot. You could hit a clamp. You might not be center on your jaws anymore. You might get vibration from overhang. So using override driving WCS lets you program a datum that never moves. So what you can see here in the code is that we've got G55, which is taken from our override. I'll show you where that is in Fusion in a second. So we're going to drive the probe from G55. We're then going to update G54. That's that S1 line in line N60 and N65. And then we're going to command the machine to move the machining moves, the subtractive bits in G54. So just to recap, we're driving the probe from G55, which is our perfect location. We're now updating G54, and then we're machining against G54. The key is that G55 never moved. And that's really important. So I go back to that image here, where the G55 is at the center of our base plate. That will never change. Even if our part is slightly to the left, slightly to the right, we'll use a dynamic offset for that and have a fixed datum here. So hopefully some of you are thinking, wow, this is going to really change the way you work. Honestly, once you get this down, it is absolutely brilliant. But I understand I've tried to cover a very difficult subject very quickly. So what I'm going to do is I'm just going to chuck in the chat a tutorial that I did for this on there. So you can have a tutorial now coming through, which is for probe WCS and for override driving WCS. So you should see that in the chat now. Ryan said, amazing, thanks, helps so much. That's brilliant. Look, if I can do this and help out one person, I consider it a success. So thanks, Ryan. I'm clocking off now. Speak to you all soon. Anyway, don't clock off, please. Don't do that. Let's go into Fusion and see how we do this. So I've got my XY probing here. So what I'm going to do is, bear with me, I'm just going to have to now change my datum that was from the top of the block. And I'm now going to do a selected point. And thankfully, that is now my new datum on the bottom, because that's the base plate. I know it's not the base plate, but surely you can work out the center of that vise goes in the base plate. Now I'm going to open up this probing up. And I'm going to go to actions. And I've already got this ticked. I've got override driving WCS ticked. So I'm going to use G55 as my static datum. And G54 is the one that's going to be updated and then machine afterwards. Now, there's some even cooler stuff in here as well. I've got out of position and out of size ticked. What do those mean? What they mean is that I'm already spending the time and the machining money in probing this part to set it up. Why not do some extra checks? It's free for me. You know, I've already spent the time in probing. Let's use that data now to get as much back as possible. So in geometry, I've got two options here, or two parameters, the tolerance for the position and the tolerance for the size. Now, I make this from 1 meter bar that's chopped up into the slugs or the billets that's then used. So what we have, though, is a problem, is the people that do our saw cutting for us throw the bar end into the box. This now means I've got a billet that will make a scrap part in my box. I need to find that. I make these normally at Autodesk University. Some of you might have, maybe some of you on the call might not have come to the London one I did, but maybe to the Vegas ones where we make similar parts. But effectively, I haven't got the time to just check if every billet's the right size. So I throw it in and I probe it. Because I've got my tolerance set here and I've got my action set to wrong size, my machine's going to stop if it's wrong. So think about this. Everyone says, oh, I haven't got time to probe. Probing is a waste of time. It's not efficient machining. I will really argue that. You're now going to use your probe to reduce your scrap. Because for one, if there's the wrong size billet in there, you won't machine it because then you're going to get non-cleanup on the sides. Or even worse, if the billet's too large, you might snap a tool. Because let's look at this, you know, our roughing is calculated from this size stock material. If it's bigger, our step over is going to be bigger and it might snap the tool. And I can guarantee you that a tool is going to cost more than the 30 seconds it takes to probe this part. Another thing, again, we look at these actions and I've got out of position. Let's say I'm loading these in and there's a clamp on the right-hand side. I've got to be careful I don't hit that clamp, because if I'm too far, I might hit that with my tool again. You know, machine downtime, you might snap a tool, you machine the clamps away, you have to change the clamps. We're all about now trying to be more efficient in the way we tackle our jobs and try and make ourselves more profitable. So I actually have a good example of this where I used to work. We had a strong hydraulic clamp that pushed up against a dead stop. Now, on a night shift, the machinist didn't realize that this dead stop had become really weak. And every time the hydraulic clamp pushed against it, it was bending it further and further and further away until the point it just snapped off. Now, if we'd have been probing with these actions on, it would have caught the fact that it kept pushing that end stop further away until it snapped off. So really interesting, hopefully something that you can do. It's not going to cost you anything. If you've already got the probe on the machine, you can start using these actions. So that's what we've got on Probe WCS. Hopefully you followed. Hit me up in the chat if there's any questions. I really want to make sure you're all happy with what we've shown so far. What we've not got is probe geometry. So that was probing at the start of the process. Now we're looking at probing in the middle of our process or at the end, but we're going to talk about it in the middle for now. So the biggest amounts of variation is normally tool wear. Now tool wear comes in two different forms. The first one being when the tool is actually used, its physical size gets smaller. And the next one is as the tool wears, the cutting edge becomes less efficient and you get more deflection. Now, deflection is where the tool is pushing away from the surface it's cutting. So you end up machining things undersized or oversized, depending on if it's a male or a female feature. How can we stop this? We can't stop it, but we can counteract it with tool wear. So what we can do is we can use Fusion now to create us a probing toolpath that's going to do this for us. Now let's jump back into Fusion and let's count those clicks again. I'm all about trying to make sure that at the end of the day, we're trying to do this more efficiently with the software than what you could do without the software. And that's the key there. Let me get rid of this one and rid of this one. I got my semi-finishing pass. So if I now wanted to try and program this by hand, I would need to turn the probe on, move to the right point. Remember it was P9814. Remember the tool number you can see already. I don't want to be doing that. I'm going to go to probe geometry. I'm going to click on that bore, actions, update toolware, and choose a reference operation. And that's really important. We're doing some quite clever stuff here. And the important one that I'm going to explain, well, there's two things. The first one is we're checking that the reference operation has cutter comp applied to it. Because if we're updating the toolware off what that's just machined, and that didn't use cutter compensation, then why am I updating the cutter compensation? I hope you understand that. We can't update the cutter compensation if we didn't just use the cutter compensation. Hopefully that's clear. So that's the one thing it's checking, is that that reference operation has got the comp applied. Now the second one is it's looking, is there any stock to leave? Now, imagine if I had a 1-inch bore and I had 0.1 stock to leave on that. 0.1 stock to leave is 0.2 on the diameter. That's now not a 1-inch bore. So if I was to program that as if it was an inch, you can guess what's going to happen. It's going to massively change the tool wear and cause us problems. So what Fusion does is looks at that reference operation. You can see here, it's seen that I've got the stock to leave applied, and it's going to actually fault the data it sends through from the post processor to tell it that's not 1 inch anymore, that's 0.98. I mean, that's pretty clever that we're doing that for it automatically. So I'm going to choose my tool and away we go. So you can see there, what was that? 1 click, 2, 3, 4, 5, 6, I think it was. So in 6 clicks, what, 10 seconds, I've now got quite a complex probing operation that's going to go from semi-finishing, probing, and then finishing. And I'm going to get a perfect part every time. There's something else I want to show you as well. What we can do is those same actions, because I can go, if I'm out of size, let's error. So I'm not only updating my toolware, I'm checking the part is correct. That's really important here as well. Let's have a quick look what this actually looks like on our machine. I'm all for the machining footage. Any of you that have seen any of my videos before know that I'd much rather be on the machine than anywhere else. So, and I do like to show that we can do what we claim we do. We don't just talk about it, we actually do it every day. And I think that does make a difference. So you can see here, hopefully 3, 2, 1, there we go. That's machined off perfectly. So we can see now that using probe geometry to update our toolware is going to improve the quality of the parts we ship, reduce the scrap, and also make us a little bit more confident. How many people out there actually really do lights out machining with multiple parts? I'll be interested to know in the chat, does anyone out there actually do proper lights out machining where they shut the doors and let the machine do its own thing while they're not there to check? Because it's something that a lot of people profess to do. We profess to do it, but we only do it on certain jobs. We really need to utilize technology like this more to get the confidence that the machine can sort out its own problems. So again, please everyone, questions in the chat. This webinar will really be changed if we can get some interaction with everyone else out there as well. Not that I'm blaming you if you don't, but you've been warned. So the next thing we can do with probe geometry, this is about updating, sorry, not updating, this is about actually getting results back. So you might have noticed that in the Actions tab, I had a little button called Print Results. What this does is get a results file from the controller. So if you've got the Renishaw macros, for example, they can make a file. You can get that off the controller and import that back into Fusion. You can now make a real graphical report to not only see what's going on for your own benefit, but you can use this to keep historical data, to track trends over time. Or you can use this to pass a part off, because we all know that it's not really viable to sit there waiting for the CMM guys to actually pass this off every time. I used to be one of those CMM operators. I never worked nights. None of us ever worked nights on the CMM shifts. So if there was ever a job set up on a night shift, they had to wait till the morning to pass it off. If we had this technology back then, we'd have been able to have passed off our own work without having to rely on someone else. I'm not saying this is going to replace the need for CMMs, but it goes a long way in giving the people who matter the tools they need to pass off their own work. There's nothing worse as a setter as doing a job and not knowing if it's right or not. You need to know, is that right? Can it go in production? Will I be making good parts? And this is how you're going to do that from Fusion and importing the results. So let's have a quick look. Got that part in here. It's called Chick Wide Faceplate Mod. There is a reason why it's called that funny name. I won't get into that now. So what I've got here is my fixture. This is actually checking the fixture rather than checking the parts that are made on it. You can see I've got loads of inspection operations. What I tend to say as well, if you've got 50 holes on a part, all made with the same drill, only check the last one. Because if the last one's right, the chances are they're all right. You know, probably if you're setting up, maybe check a few more, but just in process inspection, you only need to check the last feature that end middle, that drill made. So I've done all those. Let's go Actions, import inspection results. Now I've actually saved this onto Fusion Team. So we can just go here, go into my demos, and I've faulted the results file to get a few errors. It's not fun just looking at a sea of green. We want to see some errors on our part. So what's going to happen now, it's going to interpret that results file, look at all that data and populate it into Fusion as a graphical report. And that's really important. We've got a little preview here of what's gone on. We can look and we can see that feature 6 here is within tolerance, but its diameter is within tolerance, but its position is out of tolerance. So we can go and interrogate that a bit further now. What we've got, if we just hide that one up there, we've now got a feature list of everything that's gone on. So I can right click, show results, and now I can really start to look. We've got a combination. We've got inspect surface results that we can see here, checking a bit of this freeform area. And then we've got bores and bosses, and we've got all this data down here to show us what's going on. So we can look at the position and the error of any of these features. Now, not only is this going to let me know internally the quality of the product, but also we can start thinking about sending this off to customers. What I'm going to show you now is I'm positioning this somewhere I'm happy for a snapshot to be taken. I'm going to right click, save inspection report, call it something unique, save it to my desktop because that's where all good engineers save their work. And what I have now is a PDF emailable report. I can send this off to my customer. I can keep it in our records. The possibilities are, you name them. I have a really nice capture of a screenshot on the top, and I now have all the data for this part in this report. So you can see how important this is. You're now really using your machine tool and your probe as a proper part of your quality control process. It's not just about using it to set your data. You're using the machine tool and your probe to really be part of your QC. And that's important because what you're going to do now is you're opening up the ability to check and verify the parts to so many more people than just the ones that operate the CMMs and the other dedicated inspection equipment. So again, in the chat, we're quite quiet in the chat today. The European one was a little bit more lively than this. Come on, everyone, we're gonna wake up a little bit more. It's the end of the day for me, and I've still got a bit more energy left. But anyway, I'll stop insulting the crowd. I'm gonna chuck in the chat 2 more tutorials. This was a tutorial for the toolware and a tutorial for the importing of the macros. So if you do want to know a little bit more about it, you can go there and have a look. So now let's look. Maybe you're all a bit quiet because you're just so stunned with what you're seeing so far. I'm going to go with that one. Non-prismatic or freeform inspection. So what we've looked at before is square bosses, round holes, but unfortunately, not everything we do is a square boss or a round hole. Sorry, I was about to cough then. So what we can sometimes do is actually you do freeform inspection. So again, I'm going to be brave and pick up this mold tool. So you see this mold tool we've created? I wanted to check the features of the impression. And there's not square bosses and round holes in those features, mainly because it's a forging die. They've all got draft angles on them as well. So we're going to use inspect surface. Now, this is a bit of an odd workflow for some people. We're all used to using Fusion to create the NC code and then run it on the machine. Hopefully we're all doing that now. If not, then today's the day you can start. So we use Fusion, we create NC code, and we hit cycle start. What we're not used to doing, or not used to doing yet, is then the machine creating a file to be imported. And that's that results file that we spoke about just. Oh, apparently we're still waiting for the tutorials to show up in the chat. Okay, I can see them. I'll sort out something. Jason's on the call. He'll sort out the chat for me while I'm carrying on the presentation. Sorry that they're not coming up in the chat properly. We'll make sure they do for you. So again, this results file, we're not used to the machine creating results files, but it can. We can then import that back in as well. So what we're going to look at now is this in Fusion. Inspect surface. So inspect surface is the name of the toolpath. And what we're going to do now is we're going to go inspect surface. We're going to click on a point. And then this is the best part of the demo. We get to drag it anywhere we like. And you can see there, it's tracking surface normal. So what we mean there is what it's doing is as we probe the point, it's making sure we hit it at that surface correctly. So if I was just to come down in Z, I might get skidding where effectively it doesn't actually end up trigger incorrectly and we get incorrect results. So I now can place points anywhere on my machine. So again, the whole process, we're trying to make something where you can more efficiently and effectively now use Fusion to drive your probe. So you can put points anywhere you like and inspect that. So here's one I made earlier, lots of inspection points on there, and I've now imported those results back in. So this is what inspect surface results look like. We can do exactly the same. We can right click, we can show results, and I can interactively start looking. Let's look at all of these ones that are negative tolerance, also positive tolerance. So I've got too much material in those 3 locations. I can see what they are. I can sort by deviation if I wanted to, and I can do a bit of highlighting from there and see all those points. But I can now get a really good information back about what's actually going on with the component. So again, hopefully that makes sense. You can use inspect surface to put a point anywhere on your part and inspect from there. You can even do this in 3+2. I've got a toolpath here that's got a tool orientation, and I can start inspecting there as well. So it's not just limited to 3-axis if you've got a multi-axis machine. So again, that was inspect surface. Hopefully that's interesting, and it paves us the way onto the next topic, which is part alignment. So I wonder who else out there has had to do jobs like this. So this was an anodized part that I had to align perfectly to engrave. I could only just touch that top surface to take the anodized coating off. So you can see now how long it's taken me to do this. This is embarrassingly sped up a lot. I need to get much quicker at doing this. But why do I want to get quicker at doing this when I can use the power of Fusion to do it for me? Again, you don't want to be paying your machinists yourselves to sit there twiddling away at the hand wheel. You want to be making sure they're being as profitable as possible and using the tools that we can provide them. So how do we get Fusion to do this? It's all well and good seeing a video of me playing around on the machine, but what are the steps we need to do this? So follow me with this now. Stage 1, we're going to import those surface inspection results. Stage 2, we're going to give those results to Fusion and go, can you work out a better way of orientating this part to best suit its real location? We're going to now be told what it's like before and what it's after. Number 3, we'll be shown what the inspection results now look like. Now it's actually moved the part, because what it's saying is you thought the part was here, but it's actually here. And we get a matrix, we get told translation in X, Y, Z, and rotation in X, Y, Z. We get told that matrix that it's actually incorrect by. So that's really important as well. Now the trace toolpath on this part was a 3-axis toolpath, but you can see at the bottom there, it's put a C and an A moving to really reorientate it to its correct location. Now, I know some of you are thinking, let's shut off now, I haven't got a 5-axis machine. Don't worry. You can turn the alignment to 3-axis. You can even lock out everything other than 1-axis and just do an alignment in 1-axis if you really wanted to. But more importantly than that, if you have a 3-axis machine, we can make you a theoretical C-axis. We can do a mathematical coordinate rotation about any point, shift those toolpaths, and make sure you've got a correct part at the end of it. I've seen some really good examples with this on 3-axis machines with vacuum plates, where you put the part in, you probe that part, and then you work out exactly where it is. So let's check in Fusion and let's see how we do this. So I've got a conrod forging here, and I'm not joking. Here is the raw part, and then this is the machine part that I machined the other day. So these are real jobs that I'm doing. I'm not just talking about this in the presentation. I've got a modeled up version of the stock. I could actually have applied a surface offset if I haven't got the model, but that will all be shown later. So what I would do is go to inspection, probing, and part alignment. That now makes a new node here. And what I can do is go in, put my inspect surface toolpaths on, run that program, import the results, and now I can see the results. Let's turn off the algorithm and let's have a look how bad they were to begin with. Look at that. I've now got, this is in metric. So this is effectively, that's 20 thou negative material. I reckon that would have given me non-cleanup. What have we got over here? What's that? 0.3. That's about 30 thou. That would have given me a broken tool. And I'm really guessing it would have. These are 3D printed in 316 stainless steel. So I reckon that excess material there would have broken my tool. So I've got a combination here of having non-cleanup, excessing cutting forces because of the way the part was located on the machine bed. I run the algorithm and you can see what happens. It's now moved the part theoretically in space and found out the best location that can sit in. My results now are machinable. I can see on this graph the amount that it's rotated by. So really important there. We can see what's gone on and how it's machined it. There's something else more important here I want to discuss. I used to work in forging, as you remember from the start. We used to be riddled with problems, what we call non-cleanup or NCU. That's what the machinist sees. The forging people call it underfill. And that's where there is not enough material. And that's what we've got here. You see how this point is so far out, although the rest are still good. That's because here, there is not enough material, even though the part's perfectly aligned. So that's telling me, before I even touch this part with a cutting tool, it's going to be scrap, because that's outside of my machining allowance. So let's think about that for a second. I can now put parts on my machine and probe them, and before I waste valuable machining time and cutting wear, I will know if it's going to clean up or not. Anyone out there who's machined castings, forgings, 3D printed parts, because this will check for distortion as well as underfill, you can now tell before you touch it with a tool if it's going to make a good part. And that is absolutely an incredible. I wish we had this back when I was machining parts, back when I was doing forgings every day. To be able to know at this stage that the casting or forging wouldn't clean up would have saved so much wasted time. And that's what we're trying to show you now, how you can use these tools to make yourselves more profitable and stop wastage and scrap. So I'll get the chat right this time. I'll go to all attendees as well as all panelists, and I'll chuck in a tutorial for part alignment. So here we go. There's the tutorial for part alignment. Let me know if you can see that. Hopefully you can. So that was part alignment. Let's now go into the last topic, which hopefully is going to blow you all away as much as everything else has. So yeah, everyone can see it. Thanks, guys. Much appreciated. Manual measure. So you might not have a probe on your machine tool, and you might be joining us today to try and see should you get one. Hopefully by now you know the answer is yes. But I guarantee everyone out there has got tools like this and micrometers like this. And I've got lots of other bits on my desk that you're going to see me using in a second. And what I'm going to show you now is how you can actually create inspection routines to mean that the people doing the inspection aren't wasting time creating routines every time. They're going to know exactly what they need to measure, and they're going to be told instantly if it's correct or not. How many people here have ever seen a typo cause scrap parts? You know, I used to have to input data from paper reports, and you think, was that a 6 or an 8? If it was a 6, we're okay. If it was an 8, we've got a problem, and I've got to go and stop those parts getting shipped out. So this is really important now. We can actually make Fusion become the receiving of this data, and in real time, we're going to know, are the parts correct? There's no more, does my machine operator need to do the mathematics in his head of, well, it's measured this, And the tolerance was that, yeah, I was reading 6 upside down and it was a 9. I meant that it was a smudge. There was a 6 and it was smudged, and was it an 8? Because that was a real thing. We nearly shipped out, well, we didn't ship out scrap parts, but I was concerned about it because I couldn't tell if it was a 6 or an 8 on the inspection report. Anyway, I digress. So we're going to show in Fusion how we can now really hopefully save you scrap and give you a better workflow in Fusion. So let's jump in and let's run through this. I'm hopefully going to get some interesting things in the chat when I show this now. So this is the part we're going to inspect, and I have got it here in front of me. Again, this is a live demo. It's as live as it's going to get. And I'm going to create manual inspection. So I've just gone inspection, create manual inspection. And I'm going to choose the features I want to want to inspect, put it in a nice position, and then record that camera position. So when it comes around to doing this, it's going to orientate it for me. And that's really important because you don't want to have your hands on the keyboard all the time. Let's choose another feature. Now let's choose here. I can drag these around. I can even hold down Shift and lift them up. You get the picture. You can do lots of nice things. Let's put one more in. I've got a much neater one that I'm going to use, but I'm just showing you what we can do here. So again, I can manipulate this round. Let's go to the front view. Let's record that camera position. I can even go in and add a pass-fail item, and I can call that M6 threads. And I can check with its gauge. I can then do something like a text item, and I can do inspector name. So we know who's actually done this. And what you get now is you get a node in your browser, just like toolpaths in a folder of all these manual inspection items. So here you can see those are ones I did quickly just. These are the ones I've done before that I've given them all correct names. I didn't want you to sit here watching me do that. I'm now going to go record manual inspection, and we can see it's instantly presented it at me in a really nice position. Now, this is where it gets quite cool. I've got a set of Bluetooth calipers here. So I'm going to try and do this backwards, which is never easy because I want you to see this on the camera. I've seen this enough. So what I've got here is I've got the part in my calipers, and I'm going to press the data button, and that's going to input the data instantly and progress to the next feature. Hopefully you saw that, and hopefully there are some pretty amazed people out in the chat now, because I think this is absolutely brilliant. Being able to just sit there and go through by pressing that data button through every part I go. Yeah, we're getting some wows in the chat, and fair play. It is brilliant. And there we go. Let's do the next feature. If I can hold it on. There we go. So doesn't help. I'm trying to show you this on the camera. Sorry about that. Let's just do this properly. It's not an easy feature for me to measure while hovering it up in the air. Now, you haven't got to use these. I've got a set of micrometers. I've got a set. I've just got one of them. I've got a set, but you can just see the one. And I'm going to do exactly the same. This is not Bluetooth. This is wired. So what I can do is get it to the right measurement. I can't see that, but hopefully it's the right one. And I'm going to press the data button on here. And that's now progressed to the next feature. But don't be worried. If you haven't got all this connected equipment, you can still do this process. So I've got to measure that drop now. I've got a height gauge here. It's digital, but it's not connected. So let me quickly measure this with a height gauge. I bet you didn't think this morning that you'd be watching a Brit sit here using inspection equipment on a live stream. So there we go. Let's zero that out there. I know you can't see this, but you have to trust me that I'm doing it properly. Zeroed off the top, and now going down there. And I've got minus 14.98. So 14.98. So you can see I'm just typing the values in. 8.02. I didn't measure that one. I just progressed. So it doesn't matter if you haven't got connected equipment. You can still do this with your calipers, with your micrometers. I'm going to do the last two just because I know you want to see it even more. And then let's do the final one. I've got a vernier bore gauge here. So I have to remember my college days of how to read a proper vernier scale. So that's going to be 20.07 and hit enter. M6 threads, they're going to pass next, and then I'm going to go on to my name, R. Stubley. Let's capitalize that properly. It is my name. And okay, so what you can see now is I've got a full inspection report for this part. Now I make the next one. I just right click and go record, and I get another entry. So what you can see here is a first off check, in process checks throughout the shift, and then a last off check as well. So you can see now the whole thing is you've actually created that inspection routine once, and then every time you play that back again and get a full inspection report for your part. Just like before, I can position it where I want. I can right click, save inspection report, let's give it a different name, save it onto the good old desktop. And now I've got a printable send report where I can email it, or we can archive this digitally, and I know exactly what my part was like. So that was manual measure. I've got a few minutes left. Let's quickly have a look at what we've got left to cover. We're going to go there. Please, we've got a few minutes left. If you've got questions, start typing them in now. I really want to cover everyone's answers. So in summary, what have we looked at? We've used CAN cycles. So we've shown you how you can stop wasting precious machining time in twiddling that dial and make sure the people running the machines are doing the important things and making you more profitable. They're not there twiddling that hand wheel, setting datums. We're also going to hopefully remove potential scrap from getting datums wrong. We've looked at how to import inspection results to see what's going on. This is going to mean that you can now send reports off directly to customers. Non-prismatic inspection, put those points anywhere. Find out the quality of your part before it leaves your machine tool. Don't waste any time on taking a part off to find out it's got to go back on. Because putting a part back on a machine tool is an absolute nightmare. But if you do have to put it back on, that's where part alignment comes into play. The ability to set up complex parts quickly and reliably on your machine tool, and also the ability to know if the part's going to be scrap before you've even touched it with a cutting tool. And then finally, we looked at manual measure, not just those funky Bluetooth calipers to progress through the features, but get that consistent report every time. And hopefully heading towards that paperless shop that you're trying to achieve. So that's what I've covered so far. I did promise I was going to go through this at the start. The manufacturing extension. This is additional to the normal Fusion 360 subscription. And you can see there are a few different ways to purchase it. But the idea here is the people who do not use it are not paying for it. So if you want to use it, then you can pay that additional extra and actually use it. And I'm going to quickly end us with a case study before the question and answers. So Conchiro Prototyping are a company that I deal with on the subtractive side. They phoned me up one evening. Their saw had cut a load of billets skew or not square. They were scrapping the parts because they couldn't set them up. They phoned me and said, "We know you do some probing, can you help?" Now, it's not what part alignment was designed to do, but there's no reason why it couldn't solve this problem. So what happened here was we used part alignment and we got the parts correct. Not only did we save the amount of scrap material, but they wouldn't have been able to have made more billets because the saw was down. Now, they didn't need the extension yesterday, but they did today. So they went on, they purchased the extension, and they did. And they're now annual subscribers because they use the extension so much. So hopefully you're seeing there. I've just seen a quick question. I'll cover that in a second, everyone. Thank you very much. But hopefully you can see the extension is that brilliant. You turn it on when you want it, off when you don't. So you're not paying for it when you don't want it. If you want to know anything more about what we've covered, please follow the links in the chat that Jason sent out. And the whole point there is you'll be able to contact us. We'll be able to help you out, see if we can, look at how the software can make you more efficient and profitable. So question and answers, Salvador, multi-part inspection in one single document. Exactly, that's fine. So that's what we've got here. We've got these results. That's one inspection. That's another inspection, another one, another. These are all different parts. I could have serialized these. So I could have called that part 5, 6, 7, 8. This was part 5, 6, 7, 9. You get the picture. You can just keep importing results over and over again, and you get a new node in that browser for that part. So that's going to be part, what is it? 5680. That's 4680. Part 5680. So hopefully you can see, yeah, that's multi-part inspection inside of one document. So you can just keep importing those, and you've got a history now of what's going on. Hopefully that answers your question, Salvador. Anyone else that they've got any questions, please send them in the chat. I'd love to be able to answer them now. Come on, I'm here. Use me, ask me the questions, and I'll do our best to answer them. If I can't answer them, I'll definitely find you out the answer and reach out afterwards. Anyone out there enjoy this today? Anyone out there learn something new? I'd be really interested to know if you learned something new or something you don't think I covered that you'd like me to cover in a following live stream or webinar, and we'll happily think about the content we create. So Ryan said, learn so much, been great, thanks. Can we write out an Excel file? Really good question, Salvador, really good question. What we can do, let me just show you probably on this one. What you can do is you can right click, you can show results, and you can select all, and you can copy and paste that straight into Excel then, so you can start doing SPC on it. So you can copy and paste that data straight into Excel, and you can start doing standard deviation on the values that you see in that column. So again, really good question. Right click, select all, copy, paste it into an editor of your choice, and away you can go. You've got all the data then outside of Fusion. That was a brilliant question. I haven't had that one before. That was a really good one. Pablo saying thank you. Okay, so again, a couple of minutes for questions. If not, thank you everyone so much. I really appreciate your time today. Hopefully you've got something out of it. Be interested to know. I follow the Fusion Instagram quite a lot, so be interested to know if you're going to do anything different tomorrow than what you've learned today. And I'll be really interested to see what you do differently. I challenge everyone on this call to give at least manual measure a go today or tomorrow. Give it a go, see how you get on, and let us know. So again, thanks very much, everyone. We'll get this recording live. Really appreciate your time, and have a brilliant day. Speak to you all soon. Bye.